the Sydney SMRI, and is Renjie. Most of you are familiar with his work. He gave a talk also in the joint OSTEMS, New Zealand, US. A mathematical meeting in New Zealand last year, and he has an impressive record of publication, and especially in random matrices. And today he's going to talk about random matrices and extreme gap problems. Please, Renjie.
Yeah. Thanks for the invitation. So, I will talk about. I will give you a very quick introduction to this random matrices theory, and in the end, I will show you some of my results on the extremal gap problem. Okay, so there are 4 sections of my talk. So I will first give you several classical models in random matrices, and then I will introduce some classical result. Then I will show you some motivations from other mathematical fields where random matrices appears very surprisingly. And in the end, I will show you the extremal gap problems. So please interrupt me anytime when you have any question. So the first classical model is the Gaussian ensemble, and this is GOE, GUE, and GSE. So GOE is called Gaussian orthogonal ensemble, so which is a Gaussian measure on the space of n times n symmetric matrices. And for the off-diagonal, so they are Gaussian random variables RID, and with mean zero, with mean 0 and variance 1 over n. And on the diagonal, it's still Gaussian RID, mean 0, but the variance is 2 over n. And they are orthogonal, which means the eigenvalues are invariant under the orthogonal group action. And the second one is GUE, is a Gaussian unitary ensemble. It's defined similarly. So it's a Gaussian measure on the n by n Hermitian matrices. And the Gaussian symplectic ensemble, so it's a Gaussian measure on the real quaternion self-dual matrices, which are also Hermitian matrices, but also self-dual. Okay, so then we have these 3 types of random Gaussian matrices, and the question is, what are the distribution of these eigenvalues? And actually, the eigenvalues are real, and one can consider even more general case, which is called the Gaussian bit ensemble. So the Gaussian bit ensemble is there are n particles on the real line, where the joint density is given in this formula, and there are 2 parts of the joint density. And the first part is the Gaussian part, which is the Gaussian external confine. So there is the external field, but you have the Gaussian confinement. And the second part is the Feynman determinant, which is the internal repulsion, which is a logarithm internal repulsion. And the beta is this this parameter is the inverse of temperature in statistical physics. And if beta is 1, you just take beta is 1. So then this G is the joint density for the GOE. Beta is 2 is for GOE and 4 is GSE. And the norming constant is given by the Seiberg integral. So actually, the derived Seiberg integral for any beta is a long story. I mean, and the eigenvalues you can tell from this expression, they are repulsion to each other. So 2 particles, they can't be too close, right? It doesn't matter for the Gaussian part, but for the logarithm internal actions, if 2 particles are too close, so this means the joint density is 0. So this means 2 particles can't be too close, so they are repulsive. Okay, so so now the question is, what is the distribution of these eigenvalues? So this is the experiment you can run by your computer. So the expected density for eigenvalues. So there are the green line is for GSE, the red one is GUE, and the blue one is for GOE. Actually, these three curves, they can express in terms of Hermitian polynomials. But you can see from the picture that so when the size of the matrices agree, then these three curves tend to accumulate around this circle. Right? So this is Wigner's semicircle law. So the semicircle, okay. This is the Wigner's semicircle law. So you have n particles of G beta E, then you normalize it. You look at the average distribution of these n particles. Then in the limit is given by the semicircle law. Okay, is square root. Some people write 1 over square 1 minus x squared, and some people write 4 minus. It depends on how you renormalize your matrices. And actually, the semicircle law is universal, which means that maybe you can see this picture. So for GOE Gaussian, so which is the Gaussian orthogonal ensembles, you have the semicircle law. And if you have if you choose the n by n matrices symmetry, but the element are uniform from 0, 1, from -1, chosen uniformly from -1 to 1. So you still have semicircle law. Or you have the discrete ensembles like Bernoulli. So you still have semicircle. And for the Poisson, you see have the semicircle. So this means semicircle law is universal. Actually, you can see I give you given symmetry matrices, say ID, and the expectation is 0 and the variance is less infinity, then the Wigner's semicircle law always hold. So you just need, I think, the second moment conditions to make to make this semicircle law holds. Okay. Okay. The second classical example is circular. So the first one is a circular unitary ensemble, so which is a hard measure on the unitary group. And the second one is called COE. So COE is not a circular orthogonal ensemble. It's called circular orthogonal ensemble, but it's not a hard measure on the SON group. So actually, it's a subgroup of COE. So you take a random element from the COE, you sampled from COE, then you make the transport and times U. Then this is an ensemble it's a sample in the COE. Okay, so it's not a hard measure on the SON group. So it's still a measure on the subgroup of unitary group. So the last one is called the circular symplectic ensemble. So still is so you sampled 2n by 2n circular matrices, then you times UR times U. So R here is the reverse action, so which is defined in this way. So UR is the GNT transport and times U transport and GN, and the GN is the complex structure. Okay, so actually the similar as before. So we can consider is generally we call this circular bit ensemble. So these are n particles on the circle, and these n particles on the circle, you have the John density, and by the Seiberg integration, so the nominal constant is given in this form, and in particular, beta is 1 corresponding to the John density of John density of eigenangles with COE, and 2 is for COE and for CSE, similar as before. And the density of the C beta E is given by tends to uniform measure on the unit circle. You can see from the picture. Okay. And there's a remark is so COE and the GOE. So when beta is 2, they are quite special. They are both called the determinantal point process. Okay, so a point process is determinantal if the John density has the expression. So it's a determinant of some Hermitian kernels in this way. And for the COE, you can write down the kernels. And this GOE, you still have the kernel, right? So for here, for the GOE is KL, and the KL is the Hermitian polynomial of degree L times the Gaussian terms. Anyway, so COE and the GOE are special. So these are two most intensive studied random matrices in the field. Okay, and if beta is 1 and 4, so they are a Fafin point process, but they are not quite intensively studied in some aspect because Fafin structure is much complicated than the determinantal structure. Okay. So any question? Okay.
These are the only special cases, or it's been it is known that the other cases, for the other beta, those are not determinantal.
Yeah. So only beta is 2 is determinantal.
Only.
For others, okay, they are not. Yes.
Are not.
Beta is 1 and 4. They are called Fafin. Okay. So here is determinant, but if so, a determinant by this is a Hermitian matrix. So it's a huge n by n Hermitian matrices, and you have determinant. And for COE or GOE, this is you can write as a Fafin of some anti-symmetric kernel. So it's much more complicated than this one. Yeah. And the third model is Ginebra ensemble. So Ginebra is you take n by n non-Hermitian matrices. Okay, and each could see IJ or ID complex Gaussian. Okay. So then you can run the compute. You can run computer to see the eigenvalues of the complex Ginebra. Complex Ginebra means each could see IJs are complex ID Gaussian. Okay, and you can see from the picture that so the distributions of the eigenvalues are uniformly in the disk. Okay, so very uniformly, and actually these eigenvalues are also determinantal. Okay. Okay. So if we take other than the complex Ginebra, you can take the real Ginebra. So which means each random variables you are chosen from the real Gaussian random variable, right? So this is a real non-Hermitian matrices. So you still have n complex eigenvalues. So you can see from the picture that, so because it's real, then the eigenvalues appear in pair, but there are some particles on the real line. Okay, and you make so the numbers of the real eigenvalues, they have the expected number, which is approximate to square root 2n over pi. Okay, and this is proved by Alderman, Coston. Again, so there are okay. So there are many all ongoing projects on these real Gaussian variables, because for the complex one, it's pretty well known. Okay. And the last model is the Wishart matrices. So this is a rectangular matrices. So it's a P times N random matrices, and each element ID Gaussian. So it's a real because we choose real ID Gaussian. So then we consider the P times P covariance matrices. Okay, so G times G transport. So this matrices is a P times P future matrices, covariance matrices. So P is statistics, it's the number of the future, and N is the number of the delta. Okay, and when the limit P over N, there is a limit rho. So rho is the limit of P over N. Then the distribution of the eigenvalues is given by this Marchenko-Pastel law. Okay, so you can see from the picture. So if rho is 1.5, you have this blue curve. Then you have two edge. And if rho is 1.0, you have this red one. So the red one is very different. So you have this part goes to infinity. Okay. Actually, the Gross order is 1 over square root x. Then you have this edge at 4. And for rho is 0.5 is green. You have a similar graphs as 1.5. And if rho is 0.1 is the pink. Okay. So you can see that if rho is 1, the behavior is very different from others. So this is the left-hand side of this arrow. This for the right curves to the around 0. This is called this edge is called hard edge, and for the right-hand side, this edge is the soft edge, and similar for others. So both the blue ones, both the left and the right are both soft edge. Okay. So okay. So now I finished the 4 classical models. So then the next I will introduce some classical result. So the first one is called Wigner surmise. All is about the average spacing. Okay. So you can see from the picture. So the typical spacing between two particles is 1 over n. Right. So typical spacing is 1 over n. So this means for the bulk of the semicircle law, you can even see from the picture that for the -2 and the 2, the behaviors, the spacings are very different away from the interior. You see, so the interior, the average 1 over n. For the edge, I will introduce later on. So, but there are very few particles on the edge compared with the interior. So that's why it's called the bulk. Okay. So then, because the order is 1 over n, so then you renormalized the spacings by n. Then the limit of distribution is the average spacing. So this is given by the Gaussian-Matter distribution. So this is about the average of the spacing. Okay. And Gaussian-Matter distribution not just hold for the average, actually is hold even for a single gap in the bulk, in the interior, even for single spacing is given by the Gaussian-Matter distribution, right? So so for the GOE case, so it's proved by Tao, and the GOE case is proved by Burgat, Aldous, Yao. So this is the average spacing, and which in the bulk, which is the Gaussian-Matter distribution, which also hold for a single spacing. Okay. So this is basically about the bulk, the interior. So what happened on the edge? So this is a Bayes theory. So the largest eigenvalue tends to 2 almost surely, and actually this result holds for more general symmetric or Hermitian matrices. Okay, more general matrices, and with the moment assumptions. For example, is symmetry, and the expectation 0, variance 1, and you need the first moment is finite. So then you can show the max tends to some constant. Okay. Okay. And now this is about the convergence to the edge. So this is about the convergence to the edge. But another question is, what is the spacing about the 2, right? So what is the fluctuation around the 2, around the edge? So this is the very famous called Tracy-Wadham law. So give you the fluctuation of the largest eigenvalue. Okay. So first, the fluctuation can be expressed by the quaternion Fredholm. So give you GOE, and GSE, you can write down explicitly this fluctuation and the limit of the fluctuation. For example, for GOE, so because the max is about 2, so then you minus 2, so it's quite small. Then you rescale it by the spacing 2 over 3. Okay. So this means n tends to infinity. This is given by Fredholm determinant. Okay, and we denote it as S2. Okay, it's a Fredholm determinant by a kernel. The kernel is called array kernel, so which is expressed in terms of the array function. Okay, so this is the kernel. This AI is array functions. You can write down the probability. Sorry, the fluctuation of the largest eigenvalue in this way. Actually, for this part, it's quite easy. So it's in the standard textbook. So even the graduate student can write down this maybe as homework. But the really promising part given by the trace rhythm is, so they can further express F beta explicitly, right? So this for GUE, they can write down the F2 in terms of the solution Q of the Q, which where Q is the solution of some Pahlavi equations. So this is quite remarkable. They don't write down this limit distribution explicitly in terms of some solutions of Pahlavi equations. Okay. And for the F1 and F4, they also have the expressions. You can write down the expression very explicitly. You can see the picture. This is a picture for the trace rhythm law is 1, 2, 4. But it's quite open problems for what happened for the general beta. Okay, so only some tail estimate exist. The left tail and the right tail. So the tail estimate, the right tail and the left tail, they have it. But nobody knows the explicit formula for this general F beta. I think maybe beta is 6 or 8 is no. So this is so far maybe only 4 cases, 1, 2, 4, maybe 8 or 6. I can't remember exactly. People know, but for the general case, people don't know. Okay. Okay. So next, I will show you some motivations why people are interested in random matrices. Okay. So in nuclear physics, so this may be the starting point of the random matrices. So in nuclear physics, so the random matrices was introduced by Wigner in 1950s to model the nuclear of heavy atoms, right? Okay. So so Wigner predicted that the spacing, I mean the energy gap between the spectra of heavy atom nuclears should resemble the spacing between the eigenvalue of some random matrices. Okay, so which means the spacing of the spectra of a heavy nuclear is the similar as the spacing of some random matrices. Okay, and the experiment confirmed Wigner's prediction. Okay, so we can see from the next picture. So you can see the broken line is the nearest neighbor spacing. So which is lambda I plus 1 minus lambda I, or maybe EI minus 1 minus EI. So it's the spacing of the energy gap, Okay, so this is the broken line. Okay, it's the delta is from nuclear delta ensemble, and this curve is the spacing, the density spacing. I mean, actually, it's a Mata-Gaussian distribution for the spacing. So this curve is the Mata-Gaussian distribution for GOE. So you can see these two pictures fit pretty well. Okay. So this is for in the nuclear physics. For the number theories, so people believe that so the zeros of Riemann-Zeta functions behaves like the eigenvalues of COE or GOE. Okay, the connection was discovered by Montgomery and Dyson in 1972. So that's one purpose people study the random matrices. So we try to find the local statistics about eigenvalues of COE and GOE. Then this result are expected to hold for zeros of a Riemann-Zeta function. Okay. For example, you look at this picture again. This is about the spacing. So the line describes the spacing of eigenvalues. This line, the curve. So which is SI and the Gaussian Mata distribution of GOE. Okay, and the dot denotes the normalized spacing of zeros Riemann-Zeta functions. You can see they fit very well also. And this the next picture is Montgomery's pair correlation conjecture. So this curve is the two-point correlation functions of GUE, which is the sine kernel, and the dot denotes the correlation of zeros Riemann-Zeta function. The dot is the zeros Riemann-Zeta function, and they fit very well too. So actually, the Montgomery's pair correlation conjecture is as follows. So let's assume Riemann hypothesis, and gamma G are zeros. We normalize the zeros in this way. Then Montgomery's pair correlation conjecture is for any phi in the Schwarz space. Then you look at the correlations between 2 points, the spacing between the 2 points. I mean, the normalized point. Then in the average is given by a kernel. So it's 1 minus sine pi x over pi x to the power 2. So this is 2-point correlation functions for the COE and the GOE. Okay, so this is the conjecture, but I think it's still open. So one reference is Katz and the Senek's book on random matrices and the Frobenius eigenvalue and Montgomery. Okay, another one is I want to show you is the very surprising in the representative theory. So let the Sn be the group of the permutation group. So there are n factorial elements in this group. Okay, and we can equip this Sn with the uniform measure. So which means each element has the probability 1 over n factorial. And I pick any elements from the permutation group. And we can define Ln. Ln is the length of the longest increasing subsequence. So for example, I take n is 6. I take element permutation in the permutation group is in this way. So you look at the length of the longest increasing subsequence. The increasing subsequence, the longest one for this case is 1, 2, 4, 6. So there are 4 elements. So which means the Ln is 4. Okay. So now the question is, what is the behavior of Ln as n large? What is asymptotic behavior of Ln as n large? So this is the first result is, so one can prove that the Ln is over n square root n tends to 2. So it's quite similar as the semicircle law, right? So you have a 2, which is the edge of the semicircle law. So you can prove the Ln is a group with order 2 square root n. And furthermore, so what is the fluctuation of this Ln? So Ln minus 2 square root n over n 1 over 6. So the limiting distribution is given by the Trace-Wiener law for the largest eigenvalue of GUE when beta is 2. So it's quite surprising. So a good reference. So there are many people working in these directions on the connection between representation theory and the random matrices. So a very good reference is the combinatorics and the random matrices given by these 3 authors. Okay. So so any question? Okay. Okay. So now in the last part, so I will show you the extremal gap problems and the results so far. So what is the extremal gap problem? So the description of the problem. Okay. So other than the Gaussian-Matar distribution for the average spacing or a single spacing in the bulk, so people can study the largest or smallest spacing. Okay, if you see this picture, so on the left-hand side, so this is the COE eigenvalues on the left, and on the right-hand side is the Poisson-Pond process. Poisson-Pond process, and so we can ask this question, right? So given your n eigen angles, and what is distribution of the gaps? So the minimal gap, there are n gaps. So you want to see what is the minimal gap or what is the maximal gap. Okay, so we can see from these two pictures, the largest gap for the Poisson is much larger than the COE case. And actually, the Poisson has a much smallest gap compared with the COE. Okay, you can just see the difference between these two pictures. So the large gap for the Poisson is much larger. So I will explain why. So here, so globally, so both the process tend to the uniform measure on the unit circle. And if we want to distinguish one from another, we have to look at their local behavior. So the Poisson process, they are neutral. So the particles can't feel each other. So but for the eigenvalue for COE, the particles are repulsive. So which means for the Poisson, for the COE, the two particles can't be too close. Compare with the Poisson case. And this is actually true. So for the Poisson, you can show that the small gaps is about order n-2. And for the COE, the order is n to the power -4/3, which is much larger than the Poisson. And for the Poisson, the large gap is log n/n, but for the COE, the large gap is square root log n/n, which is much smaller than Poisson. Okay, so because for the COE, people, the particles are repulsive, right? So there are particles too repulsive to each other. So this squeeze the spacings so that the large gap can't be too large because it's pushed inside. The large gaps much smaller than the Poisson. So this is the explanation because one is neutral, one is repulsive. Okay. So for the second statement, this is a proof for the COE case. This is the disproved maybe 15 years ago. So this is the previous result on the smallest gaps of COE and the GOE. So I want to show you this result. Okay, so for the COE, so which is determinantal. Okay, so one can consider the smallest gap. So we can consider the process smallest gap in this way. So theta I +1 minus theta I, this is spacing. And we normalized by some constant by n. And theta I marked the position of the smallest gap. Okay. So why is the 4/3? I will explain later on. So if you times this 4/3, and this chi-n marked, it's a two-dimensional Pond process. So the first coordinate is about the spacings, the smallest spacing. The second coordinate is about the position where these smallest gaps occur. Okay. So this is the result by Vincent and Bernard-Hus-Brugard and Figali-Guonit. So this xn tends to a Poisson-Pond process in distribution. And you can write down the density of the Poisson process explicitly. So, the similar result holds for GOE, which I will present later on. So what one can tell from this this expression. So the chi-n tends to a Poisson. So this with some very explicit intensity. And you can see this is the second coordinate. This is the uniform distributed. Okay. So this is the remark. So maybe I can show you the remark first. The limit disposal implies that small gaps are asymptotic independence. So which means they can't fill each other in the limit. So why? Because they are really far from each other on the unit circle. Okay, there are not too many because it tends to a Poisson with the finite intensity. And the position where this smallest gap occur is uniform on the unit circle. Okay. And once you have this Poisson limit, so you have the consequence by this Poisson property. So you denote x1 to xk are the first k smallest eigenangles gaps of COE. Then you renormalize it again. Then you can find the limiting distributions about this tau k. Tau k, the rescaling his smallest gap, right? So there are many n gaps. You just label from the S1, S2 until Sn. And these Poisson properties can imply the limiting density for any Sk. Okay. So any question about this? Yeah. Okay. So the history remark is, Wilson derived tau1 and Bernard-Bourgard derived the Poisson convergence, and Figali-Guinit extend the result for some general settings. Okay, but all proofs are based on the determinant structures of the ensemble. Yeah. Okay. So next one is, so how about for other ensembles, C beta E? So you similarly, you have a two-dimensional point process, and the second coordinate is the position of the gaps, the smallest gaps, and the first one, you rescale it by beta plus 2 over beta plus 1. You're rescaling it. Okay, but yeah, in our papers, we prove that. So this chi-n also tends to a Poisson process, and with very explicit given densities. It's a Poisson with the rate given explicitly. And this, there are several factors. So this bit factor is obvious actually, because for C beta E, the fundamental determinant has the power beta. The fundamental determinant tell you the difference between two particles. So you should get beta here. But where this A beta? So A beta has a very explicit formula, and the appearance of this A beta tell you how we prove this result. I will show you later on. Okay, but for A beta, if 1, 2, 4, you can write down the constant very explicitly. But I will show you later. So A beta is the most meaningful part of the whole proof. Okay. And also I will explain why you have beta plus 2 over beta plus 1. Okay. But this result have some, our method has some problems. We can only prove this for the integer beta. Okay. But you can see that it doesn't matter beta is integer or non-integer. Okay. So then this is the conjecture. So this result should hold for any beta, not just for integer. Because of our method, we use the Sternberg integrations. So there are, I mean, you use some integer beta to derive. But we can tell from these spacings. So the smallest spacing is of order n negative beta over 2. So beta plus 2 over beta plus 1. So this is consistent with some predictions from the statistical physics. So if beta is 0, so which means the temperature is infinity, and this weak repulsion, right? So maybe go back to the very beginning. So this is the beta. If beta is small, so they are really weak repulsion, internal repulsion, and this Feynman determinant give you the distance between these two particles. Okay, that's why you should have this u to the power beta. Okay, so this is the distance between two small particles. Okay, this is that's why you have beta. And for beta is 0, so the particles are weak repulsion, temperature infinity. So we can see that the smallest gap is, in this case, is n to -2. So which is the order for the Poisson. So this means C beta E tends to Poisson if the temperature is infinity, theoretically. But what if beta is infinity? So this means particles are very strong repulsion, very strong repulsion. So which means the temperature is 0, tends to 0. So the smallest gap is of order n-1. So which means the C beta E will tend to the rigid lattice on the unit circle. Okay. So now let me explain why we have this this order. So why we have this bit +2 over bit +1. So starting point is we derive heuristically. It's not a correct proof. So the starting point is the small gap probability. So the spacing. So the spacing less than x. So for the like a C beta E, it's like in this way. So nx to the power beta +1. So very small spacing, smaller than the average spacing. So it's the probability is nx to the power beta +1. So s is much smaller than the average spacing 1 over n. Okay. Then heuristically we treat this. There are n spacings on the unit circle. So we treat these n spacings independently. Then we can have the expected, the gaps. So which is n times the number of the gaps and times the probability, which is n times nx beta +1. Okay. So if we want the numbers of the small gaps tend to some Poisson. Okay. Then this number is of order 1. So which means we must have this order. And that's why we have bit +2 over bit +1. Okay. So heuristically. And why the idea of the proof? So why we have a beta? So so assume this is the original system. So we have n particles. Original system have n particles. And we assume there are k pairs of particles with the distance in the smallest distance. Okay. So there are here. So for the x1, x2, 3, 4, and xn minus 2k. So they are in the general position. But for the rest of k pairs, they are in the smallest distance the position. Okay. And each particle in specificity for each particle has charge 1. Okay. But in the limit, if you take the limit, these k pairs of a particle, okay, will stick together, will stick to be one particle. And this means for the original one component log gas system, they will converge to a 2 component log gas system. Okay, you have x1, x2, x4 until xn minus 2k unchanged. You can think unchanged. But for the rest of k pairs, so they stick to be k particles, but with a charge 2. You have 2 different, the limit give you another log gas system, 2 component log gas system. So what is A beta to the power k is actually the limit of the partition function of these 2 systems. Okay. and all the rest. So once you have this this line, so all the rest the proof is to prove the convergence of this quotient of the partition functions. Okay, so this is where we need the Seberg integration. Okay. Okay. So any question? Okay. So the similar result hold for G beta E. For the G beta E, so you take interior and you look at the eigenvalues in the interior, and you look at the smallest gaps in the interior of the bulk. Okay. Then similarly, so we have the for bit 1, 2, 4. So this smallest gap also tends to chi, the Poisson process, and you still have G1, G2, G4. This in a similar way, and the position of the smallest gap is expressed in this. So there is a bit plus 2 factor here. So this is the semicircle to the power bit plus 2, and his remark is beta is 2 is proved by Wiesen and the who's Bourgat, and beta is 1 is by myself and my co-author. And beta is 4 is last year. Okay, so it's quite similar. So the very different is the position. Okay, so there's a beta plus 2 factor here. So which is the power of the semicircle law. Okay. Now the last question is, so what is the largest gap? So this is the result for the largest gap. So for COE, so you just labeled all the gaps from the largest one, the second largest one, and so on. And for GOE, you look at the interior, you fix the interior, the bulk, and you look at the largest gaps, M1, M2, and so forth. And they prove that. So Bernard-Hous and Bourgat, they prove that. So the largest gap is asymptotically like square root 32 log n over n. Okay, which is I show you before of the picture. And for the GUE, so you just rescale it by the semicircle law, and the similar behavior of the similar decay order of the largest gap. Okay. So in our papers, so we look at the fluctuation, and the fluctuation is so if MK is the case largest gap of the COE, and you rescale it, right? The fluctuation, so you rescale it. So it's like so n MK minus the square root 32 log n, and you rescale it and minus something log n. So then the limiting distribution is given by the Gumbel distribution. So this is the Gumbel distribution with some very explicit constant. Okay, with C1 is C0 C0 plus log pi over 2, and the C0 is 1 over 12 log 2 plus 3 cos C prime. So cos zeta function. So the derivative of zeta function evaluated at -1. Okay, this is the fluctuation for CUE. Okay, so it's given by the Gumbel, and the similarly, so you can look at the GUE, but a little bit complicated. You look at the interior of the GUE case, and you have to times the semicircle law. You rescale it by semicircle law, and you have this expression. Then the limit of the largest gaps in the interior is also given by the Gumbel distribution. Okay, so maybe it's similar as the COE case. Just a little bit complicated. Okay, so it depends on the interior, the bulk you choose. If I is you choose I, you consider the largest gap in I, in the interior is I. So if I is a symmetry, and non-symmetry, you get a different constant. But it's quite similar for the COE. So maybe let's escape these slides. So the remark is we don't know how to work for COE and GOE or CSE, GSE. Okay, we even don't know the decay order of that largest gap. Okay, so the conjecture is the decay order for the C beta E is a square root 64 over beta log n square root and over n. Okay? And the final remark is the result for the small gaps or the large gaps are universal. Okay, so they are true for general Wigner matrices with assumptions. So this is proved by Burgard. Burgard considered the small gaps and the large gaps, and also another group people they also have this universality result. Okay. So any question? Okay. So the final remark is, so this extremal spacing or extremal distance problems can be asked for other point process. For example, zeros of a random polynomial. So you have a random polynomial. If you consider the for the first one, so we look at the small gaps of zeros of a stationary Gaussian process. So it's a real zeros on the real line. So you look at the spacing. And the second one, we consider the complex random polynomial on on a surface or maybe on C. Okay. So this is a small distance between zeros of Gaussian analytic functions. And just last week, so Michini and Yakur, they post a paper about the root, the zeros. I mean, the smallest distance between zeros of a Cos polynomial. Okay. And the remark is the above papers are all about smallest distance. So the smallest distance are always much easier to study compared with the largest distance. Okay. And no result so far for the largest neighborhood distance. For zeros of a random polynomial, or even eigenvalues of a COE or CSE. So the large gaps are always much harder. Okay. Okay. So thank you for your attention.
Let's thank Renjie for the fantastic seminar. And now let's ask questions. Actually, I opened the question with one very naive, most probably question. From your graph of the GUE before, I thought that the largest gaps would appear at the extreme, and I from what I could see before, you scaled the gap between two, which is not the eigenvalue, but I would have expected that the rescaling at the extreme between 2 and lambda maximum in the GUE would follow somehow the same rescaling of the largest gap. But in that case was n 2/3. Here instead is logged by is 1 over n. So the rescaling there is 1 over n 2/3, right? Whereas the gap there is 1 over n 2/3 or something like that, is in the Tracy-Widom regime.
Yeah.
Whereas the largest gaps are of the order logged by n. So from your previous slides, I think, previous. Yeah, so here you have n to the power 2/3. And if you take the graph before, from your heuristics, you see the large gaps there. My question
in the
is...
interior. Yeah.
Yeah, sorry, say it again.
In the interior. Tracy-Widom law is globally, the largest gap you can see is at the edge. Yeah, so we look at the interior.
I see.
Yeah, that's
sorry,
why
I missed some part.
Yeah, yeah, that's why this series is so long. So you took interior,
just the interior of it.
Yes, you look at the interior. So it's not a mystery because in the interior you have the sine kernel, which is similar as a CUE.
Oh, okay.
Yeah.
Let me ask then a very naive question. If you take 2 and subtract the first eigenvalue in the interior, what's the rescaling there?
Yeah, you discard the first few. Yeah, I think this is a very good question. It's not naive.
Okay.
This is a really good question. So you want to look at I think the first few. I think the spacing is the same as the spacing of the two.
The last, and it has been proved, or is a kind of conjecture.
I don't know if there is a formula for the second. You mean the fluctuation of the second one? I didn't see it. Maybe it's proved, or maybe the third one. But I think the scaling is the same as two, but the distribution is different. Yeah, this is a very, very important question. So what happened? So you can just choose how to make this. You can choose the first few eigenvalue gaps and see around the edge and see what is the largest of that trivium. But I think this, I don't know. Yeah. This is a good question. Yeah.
Thanks, Anna. Other questions?
I have a question. Can you hear me?
Yes, we can.
This is even more naive. The semicircle law, you said the proof of the universality required the mean to be zero and the variance finite. Yep. There it is. Do you know what happens if the variance is not finite?
Yeah, so it's a good question. So I don't know. There are some people. I think there are Soshnikov has a paper on this. They choose the Cauchy distribution, and they look at the distribution. Yeah, there are some results, and I think there are some people also studied the alpha stable distribution. Yeah, there are some results. Yes, but I just didn't look at that. Yeah, there are.
The whole thing doesn't break down. Then there's still some theory there.
I think Soshnikov will prove at least you will not have this these two. I think I can't remember exactly, but it seems the largest eigenvalue will go really far. Maybe it goes to infinity, but I can't remember exactly. But yeah, there are some papers on this.
Thank you.
It's different. Behavior is different. Yeah. Yeah.
Other questions? Well, if not, let me make a small announcement that we are lucky to have Renjie in Melbourne the last week of May. So if you have a question from now to the last week of May, you might want to meet him in person. And that's it.